Sorry, I was saying that it is me that's very lucky to be here. So again, thank you very much for having me. I was also making a joke. I wanted to apologize for not wearing a tie. I was trying to be relaxed and Canadian, and I haven't had time to get back to the hotel room to retrieve my tie. Um, Today, we're going to rehearse the content of the past two lectures. I'm going to try and do that quite quickly for two reasons. One, I personally enjoyed the question and answer session in the past 2 days, so I want to leave as much time as possible for an exchange with you. But also, this presentation is going to be a little bit more fun in the sense it's going to be interactive. So the first half of the presentation is just going to be a rehearsal of the fundaments of the free energy principle, active inference, and how it leads to a kind of artificial curiosity, with a particular focus on some of the key intellectual architects that underwrite many of these ideas. But the second part, I'm going to ask you to play a game, and we're going to see how Bayes optimal you are and how good you are in terms of reasoning. And I use the word reasoning because although the game that I'm going to give you is actually a very old game, and if you've seen this game before, then please feel free to cheat. It makes my life slightly easier. But it also speaks to quite a new focus, certainly in artificial intelligence, machine learning research, which is the notion of reasoning and moving from sort of system one to system two, like thinking and cognition. So I'm going to revisit, I repeat, quite an old paradigm, which I think is becoming more current now and speaks to the deployment of the principles of surprise minimization or free energy minimization at multiple levels, and in particular about the very structures, cause-effect structures that we infer and how we effectively discover the apt structures and hypotheses that explain our lived world. So let me start with the three faces of AI physics. And I've chosen here Hermann von Helmholtz, Richard Feynman, with a nod to Jaynes, simply because their contributions underwrite nearly everything that I've spoken about in the past 2 days and will speak about today. At many different levels, it's really quite fascinating when you look at the formalism upon which the free energy principle rests, how many times you come across some foundational contributions, certainly of Helmholtz and to a certain extent Richard Feynman. So let's just start with Helmholtz. We've already seen this quote. The idea he's trying to communicate is that perception, sense making, and possibly even reasoning about the nature of our world rests upon having hypotheses, beliefs, fantasies on the inside that you bring to the fore in order to explain the way that you sample the world. So, for example, objects are always imagined as being present in the field of vision as would have to be there in order to produce the same impression on the nervous mechanism. So what he's saying here, you have to have in mind an explanation for what could have caused your sensory impressions. And clearly that's very closely related to ideas such as perception as hypothesis testing by Richard Gregory, many other examples of this analysis by synthesis, and other constructs that all speak to the brain as a statistical organ, a constructive organ, actively constructing explanations for the sensory samples. These ideas have been used to great effect by people like Geoff Hinton and Peter Dayan, who indeed built a Helmholtz machine as a metaphor for the Bayesian brain, borrowing from the notions of Bayesian probability theory, and in particular, the work of Richard Feynman on rendering what is usually, in fact, inevitably or almost universally, an impossible inference problem tractable by converting an integration or marginalization problem into an optimization problem. The thing we're going to optimize is this bound on the evidence for our generative models under which we test and build hypotheses that best explain our sensations. So let's just rehearse or revisit the history of this notion of the brain as a constructive organ, as an organ of inference. I've shown this before for those of you who haven't seen it. What you should be seeing is a bowl of fruit painted by a 16th century oil painter famed for painting still lives, that when viewed from a different perspective now gives you a very different visual impression. So now if you see a face, the point being made here is that you made that face. It's something that you have brought to the table as a parsimonious explanation that best explains this pattern of sensory impressions, in this instance on your retina, on your sensory epithelia. One way of reading Richard Feynman's contribution to this is, quite a fundamental interpretation of the what is often quoted. Nearly everybody I know always quotes this. So the meme that what I cannot create, I do not understand. This could indeed be read as what I cannot create on the inside, I cannot perceive. To understand is to have a generative model of what the cause of your sensations on the inside. And if you don't have that, not only do you not understand it, you will never even perceive or recognize it. But of course, Feynman's contribution that I'm referring to here is really about the free energy. So how does that get into the game? Well, in the first lecture, we basically saw the free energy principle unpacked. In brief, what the way that this principle emerges is just by a careful consideration of the nature of things, and in particular, what distinguishes or allows you to separate something from everything else in the universe or nothing. And we use the notion of a Markov blanket to demarcate or individuate, separate something, say a self, from everything else that was not the self, and have that as the basis of thingness when thinking about self-organization. And if we now take Feynman's path integral formulation and apply the dynamics that inherit from treating the universe as a random dynamical system or some description in terms of a Langevin equation, what we get out and apply that formalism to the partition of states implied by the separation afforded by the Markov blanket, then we get the free energy principle. Well, all what basically the free energy principle says is that if something persists with reproducible or characteristic states on the inside, open to its environment vicariously across or through the Markov blanket. So the Markov blanket both separates me from the world, but also connects me, couples me to that world. So now I become an open system, and we move from the physics of equilibria to non-equilibrium physics, and in particular, non-equilibrium steady state solutions. And those solutions enable you now to say that anything that exists, anything that possesses thingness in the sense of maintaining its Markov blanket, can be read as optimizing a variational free energy that in statistics is usually read in terms of optimizing or maximizing a bound on the evidence for a model of the causes of your sensations that is entailed by the states that are internal to the thing in question. If we take a certain kind of thing that cannot see directly its own actions, we also have a generative model and a calculus for being optimal, or for being optimal in a Bayesian sense in terms of choosing what to do next. And I've sort of expressed that here in terms of choosing those actions, that minimize an expected free energy, and we'll just rehearse what that unpacks as in the next couple of slides, based upon my beliefs about the world, my Bayesian beliefs, my subpersonal probabilistic beliefs encoded by my internal states about states of affairs currently. And that requires optimizing my belief structure, or specifically my internal states that encode or parameterize my Bayesian beliefs on my variational density with respect to this variational free energy, leading to a very simple description of self-organization as a principle of least action, in the sense that we can describe both my internal states and my active states, my autonomous states, when combined, as respectively minimizing these variational and expected free energy functionals. And that's often referred to as active inference, a description of sentient behavior or self-organization of a particular sort. So how can we understand that as an engineer? Well, the second contribution of Helmholtz was nothing to do with perception or unconscious inference, but a decomposition of flows, so alternatively referred to as a fundamental theorem of variational calculus. What we can do is decompose the dynamics of the internal states in terms of a dissipative and a non-dissipative part. Here I'm reproducing equations which we've seen previously, which describe my internal states, the mu dot, the rate of change of my internal states, might say my neuronal dynamics, if you like, as a gradient flow on this variational free energy. But this gradient flow, due to the Helmholtz decomposition, can be divided into two bits. There's a dissipative part, which minimizes the free energy, and a solenoidal or rotational or conservative part that gives rise to oscillations, cycles, replication, reproduction, whatever scale you want to pick. One particular interpretation of this Helmholtz decomposition is in terms of this inference process, this sense-making process implied by unconscious inference as described by Helmholtz, in which the solenoidal part, the conservative part, the thing that doesn't change the energy or dissipate any energy, can be regarded as a prediction if I was an engineer. Say, for example, if I was trying to understand a Kalman filter. So what does that mean? Well, it means if I know the state of the world at the moment, or if I have expectations mu about the state of the world, then I can predict how the world is going to change, and in particular, I can predict its motion, as denoted here by the mu dot here. So I have a prediction. Now, of course, that prediction may not be veridical. But I can update that prediction on the basis of what actually happened by optimizing or updating my expectations, my Bayesian beliefs about states of affairs out there, through ascending or descending the free energy, where the free energy gradients can always be construed as a prediction error, here denoted by epsilon. And that's interesting because that basically means that if you've heard of predictive coding, which has become a very popular metaphor now for understanding message passing and dynamics in the brain, then you can see immediately that there's an isomorphism between this Helmholtz decomposition that applies to anything that can be individuated in terms of possessing a Markov blanket, and predictive coding. So in some elemental sense, everything can be regarded as a predictive coder or predictive processor. So what is this prediction error? Well, imagine that you have this sensory impression on your retina, and you have a generative model of the causes of that particular sensory impression. If you had a generative model G here that could generate the sensations that you would experience if you are correct, then the prediction error is simply the mismatch. It's the difference between your sensations and that you would predict under your posterior or Bayesian expectation about what was causing those sensations. And all this Helmholtz decomposition says is that you're going to update your expectations about the world by using the prediction error to change your mind, to literally change your expectation until you've eliminated the prediction error, or the free energy gradients are zero, and you've implicitly minimized your free energy, and implicitly again maximized the evidence for your model of the sensory content. And as we've seen previously, of course, we'll never naturally know what's out there because we can only observe it partially in a very sparse way through our sensory samples via the sensory sector of our Markov blanket. What about Jaynes? Well, there are lots of ways of sort of reorganizing this free energy, this Feynman or variational free energy. I think it's nice that there's a duality between this the Bayesian mechanics that inherits from the free energy principle, which speaks to inferring the causes of observations, and the physics of measurement as articulated by Jaynes, and in particular his sort of take on the theory of dissipative structures, and in particular measurement in physics via the maximum path entropy or caliber principle. For those of you who don't know, the maximum caliber principle is just the maximum entropy principle, but we're talking about the entropy of little paths of trajectories as opposed to the states that are causing your observations that underwrite your or underlie your measurement. And you can look at the free energy principle as basically a restatement or a nuancing of the maximum path entropy or caliber principles under this Markov blanket, where we are trying to maximize the entropy, minimize our commitment to a very precise set of beliefs or explanations that best explain our data, whilst under constraints. So where do the constraints come from? Well, they basically are constraints that are supplied by our generative model. And I've just written down here the generative model in two parts, a likelihood and a prior, that when put together, they just describe the joint distribution of cause and consequence. In this instance, the states of the world S that are causing my observations O. There is often a question about, well, if you're trying to maximize your entropy, doesn't this fly in the face of the one way of selling the free energy principle in terms of trying to minimize the dispersion or the dissipation of your states and restrict yourself to a certain set of observables or a certain set of states? The resolution of that apparent paradox is you've got to be very careful about which entropy you're talking about. In terms of Jaynes's maximum entropy principle and the free energy principle, the entropy we're talking about is the entropy of our beliefs encoded by our internal states or by our measurement system. The actual observations in and of themselves also have an entropy when averaged over time. And it is when you maximize the entropy of your beliefs, you actually minimize the entropy of your observations. So I've tried to illustrate that here just by noting that the maximum path entropy or maximum caliber principle is actually a minimum entropy production principle when you're talking about the actual observations, your real states as you exchange with the world. Another perspective on this would be one which we have spoken about before, which would be that of somebody in machine learning or artificial intelligence research, where the negative free energy is the evidence lower bound that can be expressed in terms of accuracy and complexity, and can be expressed as a lower bound on the log evidence, this sort of universal objective function that is bounded by the free energy. I think it's important to just re-acknowledge that the evidence, the goodness of your models is not just how well they explain or fit the data. That's not the point. You have to do it in a very parsimonious way, in the sense of keeping everything as simple as possible, no simpler. And that's baked in to this sort of fundamental objective function that underwrites the optimization that Feynman used to solve this intractable inference problem. And that entails minimizing complexity, minimizing the divergence between your posterior beliefs and your prior beliefs. So you've got to have prior beliefs that are fit for purpose, in the sense that accounting for data accurately entails a small as possible divergence from your prior beliefs to the posterior beliefs that arise following an update in the face of new evidence. And this unpacks in terms of Occam's principle. We've already spoken yesterday about the utility or the implications in terms of computational cost and efficiency, both in terms of sample efficiency and the amount of data, say, you would need to train generative AI or a large language model, but also the thermodynamic efficiency via things like Jaynes equality and Landauer's principle. So let's just turn to the various interpretations. Again, I'm just repeating and reshowing slides as promised from the past 2 days, just to emphasize that this notion of minimizing surprise or maximizing model evidence under a generative model has a lot of face validity in relation to many other global explanations of self-organization, both in ethology and psychology and in economics and in engineering. So just to rehearse this, we can treat the probability of some outcomes that would be characteristic given the kind of thing that I am, as a score of the value or the prior preferences that I would have for those kinds of outcomes, because they define the kind of thing that I am. And this Helmholtz decomposition that allows me to treat both my internal active states as minimizing free energy means that I'm effectively maximizing value in the spirit of reinforcement learning optimal control theory, or in economics expected utility theory. If I'm an information theorist, then I can read this in an exactly complementary way as minimizing the negative value or the self-information or the surprisal, leading to things like the Inference principle and the minimum redundancy principle of Horace Barlow. Furthermore, the average of that self-information or surprise is entropy. So now we come back to the minimum entropy principle, that anything that exists almost by definition will gather its states together and keep them within a limited, non-dissipated set of states that can be read in terms of synergetics, or if I'm a physiologist, in terms of homeostasis. And of course, the story from the Bayesian mechanics perspective is that I'm going to read this probability of outcomes, observations, given me as a model, a generative model of the causes of my observations as model evidence. And that leads to evidence accumulation, predictive coding, and the Bayesian brain, and the like. So here again, we've rehearsed this before. I'll just go through it one more time, because I do think there's a beautiful symmetry here. It's not an exact symmetry, but I think it's a compelling one, at least in terms of intuitions. So the free energy, we just said, is either can be read as a mixture of complexity and accuracy. Interesting, it's a difference between the complexity and the accuracy. That is also a bound, an upper bound on the model evidence or marginal likelihood. When we move from the free energy that is minimized when making sense, when doing our conscious or unconscious inference, to actions, then we move from the variation free energy to the expected free energy. Expectation under what? Well, under the outcomes that are consequent upon me taking a particular course of action. And that expectation then now can be applied to the various components of the decomposition of the variation free energy, such that the expected complexity becomes risk and the expected inaccuracy becomes ambiguity. And in an identical way, just by rearranging the terms, we can also read the expected bound or KL divergence as expected information gain, and the expected log evidence as expected value, in the sense that it scores my preferred outcomes that have value for me. And as we have seen in the past couple of days, we can read this expected information gain in many ways. Some people like to think of it in terms of Bayesian surprise, the good kind of surprise that has this intrinsically motivating property that is renders something salient, or at least looking over there requires me to make a move that exploits or is salience seeking, information seeking. And as we'll see later, we can also apply this to understand novelty seeking behaviors. But it's just at the end of the day something that maximizes the mutual information, maximizes the coupling between me on the inside and the rest of the world that I'm trying to make sense of. And we can get back to expected utility theory by removing certain forms of uncertainty. If I remove ambiguity, we can reduce this full expected free energy minimization to something known as path integral control, or KL control in engineering, or risk sensitive control in economics, which just says that I'm going to choose those actions that minimize the divergence between what I anticipate will happen if I make this move and a priori what I prefer to happen. Or I repeat, a priori, those kinds of outcomes that are characteristic of me. I am rich, or I am loved, or I am at a certain temperature. And of course, if we remove all the uncertainty, all the reducible uncertainty from the game, we're just left with this expected log evidence, or expected marginal likelihood, or expected value, or negative expected cost, bringing us back to things like expected utility theory. So in summary, what we have is a calculus that is a necessary consequence of existence. When you read existence and you don't have to, but if you wanted to read existence as optimizing something, what you are optimizing effectively is a free energy functional or a variational bound on the marginal likelihood of you as a generative model in your universe, or a model of your universe that has to, or speaks to, the dual aspects of Bayes optimality. And very often this is referred to as a Bayesian mechanics as a complement to quantum mechanics and statistical mechanics, and indeed classical mechanics, because it just rests on exactly the same maths. Those two aspects of Bayes optimality are basically Bayes optimal decisions that inherit from maximizing the expected value, the expected log prior preferences, given my generative model, given me. At the same time, making moves on the world, querying the moves, actively sampling the world in a way that solicits those data, those observations, or those outcomes that maximize information gain, minimize my uncertainty about my hypotheses about what is causing my data. And of course, that's just an expression of the principle of Bayesian optimal experimental design from the 1950s. We put the expected value and the expected information gain together, then we have this expected free energy functional that has both these exploitative and explorative aspects to it. We've seen how to implement that in simulations. Just to reinforce the message here, that the account on offer here rests upon generative models. Generative models of the way in which your sensory data are caused, or indeed your scientific data are caused. And that's quite key, and we can have arguments about whether that the use of the word generative models relates to generative AI that we currently all enjoy in terms of using large language models. But I'm using it in a very technical and original sense, in the sense of the Helmholtz machine and Geoffrey Hinton's subsequent work. The nice thing about having a generative model is you can always write it down as a graphical model. And if you can write it down as a graphical model, there is always a factor graph that tells you exactly what messages to pass around the factors of your generative model. And by factors here, I just mean the factors of a joint probability distribution, in particular, my posterior beliefs, or the variational beliefs about the external states, or the hidden causes, or the latent causes of my sensory observations. And here are the a generic kind of generative model used for discrete state spaces when trying to simulate decision making, for example, or recognizing discrete states of the world. We've been through this before. It's very simple. I'll just take you quickly through the ABC of this. We have the world can be in one of a number of discrete states, could be a very large number, and every discrete state generates probabilistically some observable outcome through a likelihood or emission mapping, here denoted by a likelihood tensor A. But these states can change over time, and the way in which they change depends upon what I'm doing. So I can affect the world by acting upon the world to change the state transitions. So these transition probabilities, these often denoted by B tensors, depend upon what I'm doing, which depend upon my policy, which depends upon the expected free energy. And given this generative model, we can now put the probability distributions, conditional probability distributions on the nodes and pass messages on the edges in a way that has a biological plausibility. So in this instance, the belief updating has been written down in terms of what's sometimes called fixed point iteration, alternatively known as coordinate descent, or coordinate ascent if you've got the using the elbow as opposed to the free energy. These are solutions to the Helmholtz decomposition and the gradient flow implicit in the Helmholtz decomposition, and they are used usually in the context of belief propagation to simulate belief updating, which would be the discrete time solutions to neuronal dynamics. I won't go into this, but there is again, to my eyes, a really compelling isomorphism between the functional form when you actually write out the Helmholtz decomposition and the differential equations implied by the Helmholtz decomposition, and the differential equations that we use when modeling neuronal processes, and specifically using, say, neural mass models of population dynamics. And one can go into the functional form implied by writing down a particular generative model. So, for example, in this case, the model implied by having that Markov decision process that is partially observed through these probabilistic likelihood mappings. And what falls out is something which is remarkably similar to the anatomy and physiology, or the connectivity of the cortex in the brain, in terms of different neuron populations representing different kinds of things in terms of posterior expectations about the state of the world, the prediction errors, the outcomes, or the sensory afferents, and so on. So it's a really, I'm not saying that this is a solved problem, but it's a really interesting problem. It's like a jigsaw that you've given all these anatomical and physiological facts about the functional architectures and the connectivity of neuronal circuits, microscopic and right through to a macroscopic, and you've now got to sort of try and rearrange things so that the neuronal dynamics now conform to, or map in a graceful way to, the functional form of the differential equations implied by the Helmholtz decomposition under a particular generative model. So you're trying to reverse the kinds of generative models that we might entertain just by doing our variational free energy minimization. I put this graphic up just to as a nod to the fact that not all models can be written down purely in terms of discrete state spaces, and indeed purely continuous variables. And in fact, we had a really interesting lecture today at the Fields Institute, just making the distinction between sort of what and where like characterizations, that where something is as a continuous variable, whereas what something is usually a discrete variable. So in my world, when you're trying to understand the biological plausibility and implementation of belief propagation and free energy minimizing processes in the human brain, you usually have to entertain models that have both discrete and continuous state spaces in them, and that leads to a distinction between this belief propagation and Kalman filtering or Bayesian filtering or predictive coding like formulations that we saw earlier on, and how the two levels talk to each other. And there's some really interesting maths and, again, neurobiology that may shed light on the mechanisms or the way that we have evolved to evince these processes. Right, so change gear now. I've emphasized in the past couple of lectures, well, certainly yesterday, we started to address the different scales over which these free energy minimizing processes would be evident. And I just want to take that to completion today and do it in a way that hopefully will be entertaining for you. Well, it might be entertaining for me, at least. And I'm going to do that just by noting that you can apply these same principles of least action at many, many different levels to any kind of factorization of your generative model. So what I've done here is just write out this free energy functional in a way that factorizes in terms of the accuracy term, which is, there's a probability of getting some observations or data given all its causes, and the various complexity terms that then equip the free energy functional with everything that is needed to bound the marginal likelihood or the model evidence. And these extra terms can always be read as a complexity, basically a difference between your prior belief about some unknown and the posterior belief. So what are the different kinds of unknowns? Well, we don't know the states of the world. We don't know our policies that we're pursuing, but we also don't know the structure of the model. For example, the likelihood tensor here summarized with the A tensor. All of these things can be minimized. And if we just think about the different kinds of minimizations that we're talking about, we can think of optimizing Q with respect to the variational free energy, Q over the hidden states of the world, as basically inferring latent states or hidden causes in the spirit of active inference. But we can also apply exactly the same mathematics, if you like, to the beliefs about the parameters of my model, say, for example, the likelihood mapping, at a slower time scale, leading to something called active learning, exactly in the spirit of David McKay's active learning, and indeed going right back again to the principles of optimum Bayesian design, Dennis Lindley in the 1950s. And of course, what that just leaves now are optimizing beliefs about our precision, and we can refer to planning as inference as summarizing that kind of free energy minimization. But what I want to focus on is optimizing not the posteriors, but the priors. So here's a subtle twist here. Notice that the free energy principle, sorry, the variational free energy is a functional not just of your posterior beliefs that you can infer and learn about or optimize through inference and learning, but it also depends upon the priors, which means that I should, in principle, be able to optimize my priors to minimize my free energy or maximize my marginal likelihood. And this leads to this interesting notion that you can apply active inference or the free energy principle to the structure of the model entailed by the priors, and I've referred to that here as active selection. And that's basically what I want to pursue for the remainder of this talk. And I'm going to pursue it in a way that engages you. So what I'm going to do now is invite you to play a game. And this game basically is going to see how Bayes optimal you are. And it's not about inference, it's not about learning, it's about selecting the best hypothesis or rule or symmetry or invariance or structure that accounts for all the evidence that I'm going to present to you. So it's specifically, this is the game that I'm going to ask you to play, all of you. The idea is we're going to see how many trials or exposures, how sample efficient you are before you collectively or one individual manages to discover and select the right rule. And then we're going to apply these equations that I've just shown you to this exactly the same game with exactly the same prior beliefs and see whether you can beat the in silico agent or whether it can beat you. So we'll see how base optimal you actually are. So here's the game. These are your prior beliefs. This is what you know. I'm going to present 3 colored balls, and your job is to choose the correct color. Choose the color of the ball that you think is the correct color based upon the arrangement of the 3 large circles. And I'll give you another prior belief. I'll give you a clue. The location of the correct color depends upon the color of the upper circle. So in this instance, the location of the correct color depends upon blue. I'm also going to show you just so that you can see, you can accumulate the evidence so you don't have to remember the correct colors on subsequent trials. I'm going to indicate what the correct color was for this particular trial of this game by circling the correct color in magenta on 3 little balls below. But you should be focusing on the 3 balls there. Is that clear? Has everybody got the game? Yeah, good. Right, well, let's start playing it. And I repeat, the idea here is to we're going to see how quickly you can get it collectively. So here's the first, here's a collection of games. I'm going to work through them from game, I can't see my mouse, where are we? Here we are. From game 1 through to, well, however many games we want to entertain. Right, so central color is blue. Anybody want to guess what the correct color is in this first game here? Green. Let's just see if you were right. Oh, well done. Who said green? I know. It was very. I know. You didn't have to confess that. You could have pretended you were really, really clever. But of course, you have absolutely no information at this stage what the rule is. They're going to be pure guesses. So, but that's very clever. Well done. So, do you want to? The next one is the central color is red. Do you want to take a guess as you want red, dear? I'm sorry, it was green. Have another go. 3rd time lucky. Yes, of course it's red because there's only red on the board. Right, who said red then? Right, so now the center is green. Would you like to hazard a guess? Well, somebody was clever, so there's two. Right, who wants to go next then? Oh, hang on a second. If anybody thinks they've spotted the rule, put your hand up. Okay, 1, 2, 3. So before we test the hypothesis, Camille, do you want to tell us what you think the rule is?
So first time it will put right one with B, and the next time it's 3 because of the left. Next time it's just letter, that would be right one, and then now the left one again, so B. So the next one is the right one, 3. And
You're so clever. You're absolutely wrong, but very clever. Now, remember that because, if you like, that's Bayes optimal jumping to conclusions. And it is something that we are exposed to, even if we're Bayes optimal. So just remember what you just did there. Can I ask, does anybody have another hypothesis that was not that hypothesis? So everybody thought it was that hypothesis. Anybody else want to hazard a guess? Why don't we test the hypothesis? What do you think it's going to be now? John? What? You were wrong. Right? You, what do you think? Yes, what color? Well, that's very clever. Did you have a reason for that? What would... Again, a very plausible theory. So remember, that was at trial number 6, and you committed to a particular hypothesis. You were at number 5, and we're currently at number 6. But no, that was not the correct rule. That's nearly right, but not quite. Not quite. Why don't we test that? What do you think is the correct color in this trial here, trial number 7? You think it's going to be red? By Jove, she's got it.
So I think because in the first figure, because it says the location of the correct color depends on the color of the upper circle. The upper circle is blue. Then this one, the correct color is green, so it's on the right side. Then when the the upper circle is red, then the correct color is on the left side. When the upper circle is green, then the location of correct color is just the upper circle. So in the 4, 5, 6 is green. Then one is blue, you look on the right. One is red, you look on the left side. Is it?
Well done. That's brilliant. That is the correct rule. Now, can we just count? So when did you realize that? Was that after 6 or 7? After 7. Marvelous. Okay, so now what we're going to do is take you through a synthetic agent solving this task and see if they can get it in 7, and see whether you win or whether the synthetic agent wins. So how do we? Oh, yeah, let's just confirm that rule was the correct rule. So when simulating this, we have to attend to the real practical issues. So the agent in the simulation has to actually choose where to look. So the actions are both where do I look next and do I select a particular color or not. So I'm just reminding myself to remind you that the detailed specification of the generative model and which factors are controllable also has to include the way that the agent gathers the information to resolve uncertainty. And that's important because if the agent wants to make a quick decision, if it knows, like you, the rule, then it will always go to the center to find out where the correct color is, so it knows where to go next. So it's like a 2-stage task that involves some epistemic foraging. But if it doesn't know the rule, then it may not know how to deploy that rule. So how do we write down that generative model? Well, it's very simple. We just have to list what the agent can see, and or everything we need to know in order to generate those observations. So the agent can, depending upon where it's looking, it can see the starting position or a particular colored ball. It also can feel where it's looking. It could be looking at the start position, which is a gray here, or at the left, right, or the center. And it also receives some feedback, right, wrong, or null if it hasn't actually committed to a particular color at this point in time. So what would cause these outcomes? Well, I need to know I need to know the correct color, and I need to know where the correct color is indicated. I need to know where I am looking, and I need to know whether I have chosen or not. And given all of these latent causes or hidden states, I can always generate what I would see. So I know where I'm looking, I know what the correct color is, I know the context in which I'm working, then I can generate probabilistically the correct color. And I do so with some lawful likelihood mapping. So I've tried to, this is a tensor, so it's got a number of attributes to it. I try to summarize the nature of these asymmetries or rules or structures that we bring to the table in order to make sense of our to make sense of our world. That has rules, that has laws in it, that has structure, that has physics, has contingencies. And the particular contingency here is very simple. It's just that there is a lawful relationship between the color I'm seeing and the correct color when and only when I'm looking in the right place. And the right place is conditioned upon or signified by the instructional cue, which is the color of the center cue. So this likelihood mapping, or this sort of unwrapped likelihood tensor, illustrates what it is to be a rule, to have a symmetry, have some invariance. It's basically a sparse lawful mapping that is conditionally dependent or context sensitive. And in this instance, I repeat, the context is supplied by an instructional cue, which is the color of the center But you knew that the color of the center was the instructional cue, so you knew that there was some context implied by the color of the center. What you didn't know was what that meant. So you started off with these priors with no structure, with no sparse lawful mappings or identity mappings or isomorphisms, and you were trying to infer this particular structure, which is the rule that you so gracefully identified and described. So that's the generative model. So we can now take this generative model and give it a series of games. I've given it the 32 games that we had on when we actually played the game, and this is its this is the results of it trying to infer or behave in a way that will result in what it prefers, which is to be right. It prefers to be right and doesn't like to be wrong in terms of the feedback. But of course, it has to acquire and seek out information using this epistemic foraging or expected information gain in order to even choose what might be the correct question, and build and learn this likelihood mapping by experience, enabling it to try to make the correct choices. And it doesn't do too bad. So here are the correct colors, and here are the different policies: looking to the center, looking to the left, looking to the right, looking to choosing, enumerated, and it sort of depending upon the cues, it sort of selects the appropriate policies. And initially, and I should say this agent was allowed to keep on making mistakes until up until 4 moves, 4 choices. And after about 13 trials, it stops making mistakes. So there's enough information in its foraging for it to, with a relative degree of confidence, identify the correct color with no mistakes after and only after 14 exposures. So that's encoded here. The confidence is actually measured in terms of the the entropy or the neg entropy of the belief distribution over the policies. My apologies, I've lost the screen on this computer. And that's the accompanying free energy, which is minimized after a period of learning. So that's really interesting because you did it in 7. This has taken twice the number of exposures. So that begs the question, how on earth did you do that? But before we try to address that question, I just want to sort of take you through some of the neuronal correlates of this simulation because they're quite interesting. I repeat, the belief update schemes that we were talking about rest upon this Helmholtz decomposition that can be read as neuronal dynamics of a biologically plausible sort. And indeed, we can simulate event-related potentials during the belief updating, induced or evoked by presenting different cues and indeed saccading to different parts of the scheme. The interesting thing is, once the agent has learned the rule, the meaning of the colors is revealed to it. And that meaning means that it is able to belief update. It can update its beliefs about the particular context in which it is working and what it is going to do much earlier relative to when it didn't know what the rule was. And that is manifest in terms of evoking responses to salient cues much earlier in a trial after it has learned the rule relative to before it's learned the rule. So literally the sort of the electrophysiological or simulated electrophysiological correlates of meaning. Meaning that has been acquired by inferring an appropriate likelihood mapping, but through this process of active learning and active inference. But the question you could be asking, well, why does the agent look anywhere if it doesn't know the consequences or doesn't know what the rule is or how to get its preferred outcome? And of course, the answer, we know the answer, it's just the resolution of uncertainty or the epistemic foraging. But we can extend this notion of epistemic foraging not just to the states of the world. In this instance, what's the correct color? What's the context in which I'm working on, which is signified by the central cue? We can apply exactly the same maths to the likelihood parameters. So now we've got exactly the same kind of information gain, but we're not gaining information or resolving uncertainty about states of affairs. In this instance, the location of the correct color, but the parameters of the generative model in and of itself. And this is the rule in and of itself, or the contingencies that underwrite that rule. And we can think of this difference in terms of the expected information gain about the parameters as novelty, as opposed to salience. So in my world, novelty seeking actually means making moves that will resolve uncertainty, not about states of affairs, but about contingencies. So it's not, I'm not opening this door to see what's behind it. I'm just opening this door to see whether I can open the door so that I can update slowly all the laws and contingencies that characterize and parameterize my generative model. And active learning is just an expression of that I am, in minimizing my expected free energy, I am compelled, or I will choose those actions that are inherently novelty seeking. So put that simply, what happens if I do that? There is an epistemic allure, however dangerous. Right, so let's come back to the agent. So you beat the agent. I mean, you did personally, but collectively, you also beat this Bayes optimal agent. You got it in a handful of trials, in 7 trials today. How on earth were you able to do that? Does anybody know? How is it possible that you could do this? Whereas if I apply Bayes optimal belief updating, it takes, with that exact set of cues, 14 moves in order to stop making mistakes.
Because we have like deterministic rules, so it's always a very strict and logical thing. While the agent is always modeling it probabilistically. So there could be, you could kind of trick us, or there could be some probabilistic relationship.
Yeah, I think that's absolutely right. You knew there was a rule, whereas this agent didn't. It just knew there was a likelihood mapping. But you have this sort of hyper prior that the form of that likelihood mapping, in your words, had a logical, deterministic, lawful structure. So there were some elements that won and other elements that were all zero. But this was itself context sensitive and it wasn't everywhere. So the very fact, so what you're saying is, we know that our world has these laws, these symmetries, these rules, these invariances that are characterized by this sort of sparse structure and usually very context sensitive structure. And just knowing that means that there's another level of active inference, if you like, or self-evidencing that we can apply now. And that level is basically this active selection. So can we simulate that? Can we get this agent to perform as well as you did? Well, let's see. Let's think about how we'd actually implement this kind of active reasoning, system 2-like reasoning. It's active selection, hypothesis testing explicitly, where we know there are a discrete number of hypotheses that are lawful and have this sort of this particular structure. And the way that it's implemented in terms of active inference is to just focus on the novelty term and the complexity due to the structure or the nature of that likelihood mapping, the structure of this emission probability matrix here. And in particular, just focus on the prize. Now, remember I said before that the free energy is a function of the prize. So that means I can change my prize. I can say, oh, I thought the world was like this, or I thought the world was like that. And what I can do is I can go and put my prize back to all the data that I have collected so far and work out what the best prize would have been had I been able to choose them before acquiring the data. And effectively, if you remember before, we're talking about minimizing complexity is the game of choosing posteriors that provide an accurate account of the data, but are as close as possible to your prize. This turns it on its head and says, well, we can also now move our priors closer to our posteriors. In this instance, posterior is about the likelihood and the structure of the likelihood. So what would that look like in practice? Well, to do that, we've got to actually equip the agent with a number of hypotheses. You know, if you're a scientist, you just have two, your favorite and your null hypothesis. But in reality, we probably entertain a large number of hypotheses. In this instance, I've just put these lawful identity mappings in different combinations in this motifs in this likelihood tensor. I think there are about 64 possibilities, different kinds of rules, which probably would have included. Actually not, no, you were a bit clever. You were actually thinking about trial to trial dependencies. So that wouldn't have been part of the part of this. It's a simpler set of rules, but they still have the the same lawful dependency that was implicit in your rule. And if I give it 64, then we can use a process called Bayesian model reduction to rifle through these priors and see which one of them would have maximized the marginal likelihood in the face of the data that I've already seen today, for example, or literally in the past half hour. And this basically, I repeat, implements something called Bayesian model reduction, also known as structure learning by people like Josh Tenenbaum and radical constructivists who like to think about the problem of identifying the right structure of the generative models and how you explore those spaces and how you identify the best kinds of structures. I like to look at this in terms of processes like sleep. So the idea here is that we accrue all this information, we do our active learning, we sort of accumulate in the simulations Dirichlet counts, but you can also think of it in terms of experience-dependent plasticity, as we've seen co-occurrences of this and that, and we acquire during the daytime connections or associations that make our model more complex but very expressive, and we can create an accurate account of the data. But then at night time, in the absence of any sensory input, the accuracy term goes away. So to minimize my free energy, I now have to minimize my complexity, because there is no accuracy, because there's no outcomes to be accurate about. But I can still minimize my free energy or self-evidence by reducing the complexity, just by finding the simpler explanations, by putting these different priors in play to find the model that has the maximum marginal likelihood or model evidence, or the minimum free energy. And what this looks like effectively is pruning away those parameters I don't want. So those zeros on the off diagonals of my lawful parts of that likelihood mapping. I don't need those, they're redundant. So I can get rid of them. I can prune my model while asleep, minimizing my complexity, that best accounts for the data that I've seen during the daytime. So I now don't overfit tomorrow's data. And basically what I've just described is one account of sleep, but also you could think of doing this online just by thinking about stuff, introspecting, closing your eyes, and just sequestering yourself from sensory evidence and thinking about it and trying to find a simpler explanation, a more parsimonious, oh, it's just what this and that are just instances of the same thing, and thereby gaining insight into the symmetries and the lawful structures that govern the generation of our sensorium. So this is what happens when we now equip this agent with this capacity to introspect, to have a little nap between trials and work out, is there a better prior that could have been brought to the table to explain my sensory observations? So here's the true mapping. Here are my priors. Here, after 12 moves, are my posteriors without and now with my capacity, knowing I have rules, just knowing I have a repertoire of rules, and one of them is a better explanation than the others, means I can vastly accelerate my inference and get to the correct rule in a handful of trials. And so how many trials did it take? So I've cartooned that here at the bottom, asking 64 synthetic subjects to play that game and other games. And what I've done is, when they realize, when they have this aha moment, which is suddenly finding the right, this is clearly the right prior, the right structure to explain, I've denoted that with a magenta blob. And when they've got the wrong, so very much like you jump to your conclusions, that there is a plausible explanation for what I've seen so far, and I'm going to commit to that. I've given it a blue here, so that does happen. There is you can't be guaranteed. This is just inference. You can sometimes get the wrong rule that provides a great explanation for what you've seen so far, but doesn't necessarily explain what you will see in the future. And when we do that, we now happily reduce to exactly the medium which you demonstrated for us, which is 7 moves. So now we had to replicate your insightful, literally insightful inference and reasoning. We've had to tell the model there are rules, and more than that, we've actually had to give it a library of potential hypotheses or rules to, I repeat, rifle through to get the kind of performance that we enjoy. So in summary, then, there's 3 phases of AI that emerge from this sort of decomposition of the variational free energy in terms of different factors, but also over different timescales, means that we can summarize reasoning in terms of minimizing uncertainty, where the sources of uncertainty are the latent states or hidden causes of our sensory input, the parameters of the generative model generating that input, and the very structure, the latent structure of those models. So effectively resolving uncertainty at those three distinct levels can be considered as inference, learning, and selection, technically Bayesian model selection. And we can read this as different kinds of artificial curiosity driven by salience, novelty, and knowledge that needs sleep. So, last word to Einstein: everything should be made as simple as possible, but not simpler, emphasizing the importance of keeping your prize and your posteriors close, either through minimizing complexity or updating your prize judiciously. Furthermore, the important thing is to not stop questioning. Curiosity has its own reason for existing, speaking to the importance of expected information gain in determining the most likely thing that we are going to do next. And that's it. Again, thank you to my colleagues, and to thank you for attending and for playing that game so expertly. Thank you very much indeed.
Thank you, Karl. So we had an excellent Q&A last night, and I think we should attempt to replicate that again. If we could get the other mic working now, great. Then I'll wander around with this one and hand it out to folks with questions. I'm gonna grab the first one, but pop your hands up now, people, if there's any questions burning. Any questions from the audience? Okay, we'll stew on that. Karl, point of clarification, and then maybe you could jam on an idea. So you had an equation fairly early on. I forget exactly what you labeled it, but it was separating, it's like derivative of u. You called it Helmholtz something. Point of clarification, it kind of looked like a Helmholtz equation. I know you're kind of calling on Helmholtz 50 different ways here, but a Helmholtz equation separating time, or a temporal component and a spatial component in the sort of standard physics interpretation of Helmholtz equations. Yes, right. The d, equals du nabla g there. So it looks like you've separated. It looks like you kind of separated time and space there, or that would be an analogous. Would that be an analogous kind of way of looking at that? That's the point of clarification. Then the question is about temporal fluctuations. So you've written elsewhere, you indicated earlier, like I think today, but maybe this was more in the previous two lectures, about thinking about the inference process within this framework as a type of statistical mechanics, dynamical system. And those processes have some frequency content, some temporal content, and can even be framed in terms of their spectral content. And even coming back to our 3-day workshop, they have some modal structure, or at least they have an eigenspectrum that maybe describes its temporal structure. So is there something useful to say about the temporal signatures of the active inferencing agent? And I also thought, when we come to the sleep example at the back, at the end there, agent in the pruning mode versus in the sensory interpreting mode, maybe are there differentiable signatures when you have the different components of the terms turned on? So riff on that while the rest of the audience tell me who's coming next. Well, I think you've got a mic there, and I'll go to where the next question is coming from, if I can see some hands. Great, Maurizio.
Right, in terms of riffing, so no, I am not separating space or time. I wouldn't dream of doing that to you. But there is a nice separation that you've identified here, and that's between the dissipative and the non-dissipative parts of the flow. So in that sense, there is a sort of separation in the sense that if I keep going around in circles, then I'm not really evolving or moving in time. Whereas if I'm flowing down free energy gradients, then I am evolving in time. So I think in that sense, you're absolutely right. So all we've done here, that Helmholtz decomposition, and I should say that, of course, that just applies to sort of three spaces. So technically it's called the Helmholtz-Hodge decomposition, that generalize it to any sort of any vector flow. You can always decompose any flow on anything that's been conserved, for example, in this instance, probability mass, or in hydrodynamics. Well, in fact, more generally, you can always decompose any flow into a gradient flow down some Lagrangian or some potential. In this instance, it's the surprisal or the free energy, and something which is orthogonal to it and circulates on the isocontours of your potential function or your Lagrangian, in this instance, the variation free energy. So again, this solenoidal flow, this conservative flow that circulates on the isocontours of your free energy landscape, is timeless in the sense you're not moving things on, and you're not dissipating, you're not even actually using any thermodynamic work to do your belief updating, does represent this sort of timeless aspect. So again, I'm trying to riff in a way that sort of speaks to your sort of separating this, your temporal versus non-temporal. So of course, the prediction that you make in the absence of any data that will allow you to actually minimize your surprise or free energy, is an energy effortless. It's just what will happen next. So I can make the prediction before I actually sample the data to do my dissipative free energy minimizing gradient flow, and I can associate that part with the solenoidal part. So all we've done here is take Q and gamma, where gamma indexes the amplitude of random fluctuations, and put the gradient on the inside of the bracket. So we've got Q times a gradient, and that's zero by definition. That's what solenoidal flow does. Well, that's not quite true, but and then gamma times the gradient, and I'm rewriting the gamma times the gradient as in terms of the prediction error. Why that is important in terms of eigenmodes, what it means is if you think that at the end of the day, if you want to describe the dynamics of any system and summarize them, you're basically looking at the eigen solutions of the Jacobian. What the Helmholtz decomposition allows you to do is to separate the Jacobian into symmetric and antisymmetric parts, which means now you've got the real part of your eigensolution and eigenvalues on the one hand. That's a dissipative free energy minimizing part. And then the complex part are the oscillations. It's a solenoidal flow. I think there's, again, a very beautiful and simple mathematical utility to the Helmholtz decomposition, because it just shows you immediately that you can always separate the real and imaginary dynamics in terms of the, in terms of a linear stability analysis, for example. What it also tells you, as soon as you've got this solenoidal flow, you've got the imaginary parts to both your eigenvalues and your eigenvectors, which means you have to have oscillations. Possibly not sinusoidal, but you have to have some complex dynamics that you can read now in terms of oscillations, which means that there's now a close connection to the study of oscillations as spectra from the point of view of the eigenmodes. So I think that's one nice utility of this, and on that view, you would now regard the prediction part of a Kalman filter or predictive coding as, if you like, the solenoidal part, and the gradient flow now as the belief updating part. Just practically, one of my favorite sort of practical applications of this, if you want to think about what happens when things get nonlinear, sometimes it's the case that the solenoidal part can actually augment the gradient descent. So it'd be like sort of going around the edge of a valley, trying to find a path down. From the point of view of optimizing dissipation, for example, it'd be like stirring your cup of coffee to disperse the milk or the sugar. So you get this notion of solenoidal mixing that may be an essential part of self-organization, where the quality of the self-organization is read in terms of the degree to which you can minimize your Lagrangian, your potential, or your free energy, or maximize your marginal likelihood. So you could read solenoidal flows associated with things like evolution, or indeed breathing, or indeed saltatory periodic sampling of the world at a theta rhythm with our eye movements, or auditory in terms of generating phonemes, as evincing a kind of solenoidal mixing in terms of resolving uncertainty doing the gradient flow. Is that a good enough riff? Is it, what else were we into?
Yeah, that was pretty good for me. I mean, that's fascinating. I think that's a really interesting part of the picture, the dynamics of inference. Maurizio.
Thanks, Karl. So I have a more general question that hopefully will help to interpret, at least for me, the framework that you're presenting. So one is a very practical one. So everything for me reduces eventually to heat, metabolic cost, right? And could you help me interpret how the metabolic cost of living, of the rational processing, of cognitive processing, is factored in this overall framework? I assume free energy here is not metabolic energy, it's something that includes metabolic energy, but eventually, if minimizing the minimizing entropy, or minimizing the variation of free energy, right, implies practically a metabolic cost, I assume it can be very costly. So not necessarily we go towards the simpler solution, right? Because it might be also the costlier. So maybe we compromise. On a more fundamental level, so more on the classical thermodynamics, I couldn't avoid here to link your general framework to the glorious Prigogine idea about self-organizing systems and the thermodynamics of life. But again, is it reasonable for you to think about the minimization of free energy as inevitably a maximization of the entropy in the classical sense? Or where is essentially entering this neg-entropy idea that Prigogine used for allowing the ongoing living of the system, and in this case of the brain itself, as you formulate?
Yeah, excellent questions. So the technical answer to your question is that the variational free energy plays the role of a potential. Hello? Oh, that's better. Yeah, thank you. Sorry, I was saying the technical answer to your question about the thermodynamic cost of belief updating is fairly straightforward and very interesting. So the free energy plays the role of a bound on the self-information, which can be read as a Lagrangian or a potential function. So whenever you do any information processing, you're doing some Bayesian belief updating, which just means you are moving on a variational free energy landscape, which just means you're changing the potential. So the amount of thermodynamic energy that is entailed by changing the variational free energy through a process of Bayesian belief updating is can be evaluated in joules just by applying Boltzmann's constant and the temperature. And the Boltzmann's constant is just a constant of proportionality that renders the temperature equivalent to the amplitude of random fluctuations in which you are making that inference. And interestingly, it shares exactly the same as the Landauer limit. So if you do some belief updating by changing your free energy by 3, that's about 4 times the Landauer limit in terms of the amount of energy it takes to do that. The reason being that the Landauer limit is this 1 bit of belief updating, whereas 3 natural units of free energy is about e to the power of about 20, which coincides with what statisticians use. For example, having a log base factor of 3 would correspond to believing something with a p-value of 0.05 or 1/20. So that, you know, the semantics of changing the free energy, or, you know, the amount of the information distance you move on that free energy landscape has a direct interpretation in terms of how much you've changed your mind, and also a thermodynamic cost. And then you can read that in terms of things like, well, the way that people like Jeremy England might read this, that you've got to spend energy in order to do your belief updating. And the way that the free energy principle is applied is to say that in maintaining myself in a non-equilibrium steady state, I can be described as minimizing my variational free energy, which costs thermodynamic energy, which is then expended to the environment. And I repeat, just by appeal to the Jaynes equality, you can enumerate that, and it, you know, in generalizing Landauer's principle to systems that are open and changing slowly, and apply exactly those things. So there's a really interesting relationship between the, you know, speaking to sort of it from bit notions, between the belief updating described in terms of movement on a variational free energy landscape, and it's not the statistical thermodynamics, because you'd have to have an ensemble assumption for that, but you can certainly read that belief updating from the point of view of stochastic thermodynamics of a single path, from the thermodynamics point of view. And the second, Prigogine, and I sort of take my lead from Jaynes, who sort of revisited in the 1980s distributive structures from the point of view of minimum entropy production. So I always get confused by this, and everybody else I talk to gets confused about, you know, maximum entropy. Why on earth would you want to maximize the entropy? But in fact, what he meant was it's a minimum energy path entropy, a minimum path entropy production principle when applied to the actual measurable paths. Is that interpretation fully formal and licensed? I don't think it is, because neither Prigogine nor Jaynes had the Markov blanket partition to play with. So all of these formalisms in the 20th century do not fully accommodate the fact that you are open to a system in a particular kind of way. So the free energy principle, if it stands slightly alone, simply be in virtue of the fact you've got this 4-way partition between internal states and external states, and the blanket states that play the role of a heat bath. And it's really the relationship between the internal and the external that we're talking about, whereas the heat bath now becomes the blanket states. So I can't say that, you know, the free energy principle is Jaynes's maximum or minimum entropy production principle, simply because he did not articulate a distinction between blanket states and internal states and external states, and neither did, you know, no one else has, to my knowledge.
Giuseppe. Thank you. Following up on John's question about eigenmodes, maybe this is stupid, but I was thinking, you know, in physics, there's Hamiltonian mechanics, and you have a lot of complicated but very fascinating things like for example, Noether's theorem, I don't know if I'm pronouncing this correct, that relates symmetries to conservations. And to prove all this, you need Poisson brackets and complicated things. But then when you move to quantum mechanics, all that becomes very elegant and simple in terms of simple linear algebra equations, like the Schrödinger equation. And also the conservation and the symmetries become simple, you know, linear algebra, like the commutator between operators. And I don't know, I was thinking if you think there's a way to do this in the free energy framework.
Yeah, well, I do, but and also a lot of my colleagues do. So yeah, there are a number of ways I could read that question. And just to put a bookmark on it, I don't know where's John. There, yeah. There is something fundamental about eigenmodes and the free energy principle when it comes to what when you think about the nature of things and the states of things. Ultimately, you have to appeal to the renormalization group, and the RG operators are just the eigenmodes of blanket states. So there's something really fundamental about eigenmodes behind all of this kind of physics, if you like. So I just wanted to say that before forgetting that. In terms of the sort of the quantum stuff, I think there are two levels that one could say yes to that question. The first one is if you abandon any generative model that is equipped with priors of a metric sort and move to a discrete state space model that can then become a Hilbert space, then you can speak to quantum information theory and indeed quantum mechanics. And as you say, all of the operators are simply sum product linear algebra operators. And that's the beauty of working with these discrete state space models. So all the operators, if you remember those fixed point iterations, they were just, with the exception of the softmax operator, then they were just linear algebraic operations in belief propagation and variation message passing, usually subsumed under the rhetoric of sum product operators, but they're just tensor contractions. So it shares exactly the same beauty and simplicity as quantum mechanics. But you have to go to discrete state space models and, if you like, coarse-grained Hilbert spaces to do that, which is why a lot of people like to work with these discrete state space models, because of exactly that simplicity. There are prices to be paid in terms of the numerics, but algebraically, they're lovely to work with. The other way of looking at this, though, is to not worry too much about quantum mechanics, but to worry about quantum information theory. So if you're really interested, you go and read the work of Chris Fields, who has a quantum information theoretic interpretation of the free energy principle. And he just reads it as basically the principle of unitarity, and reads the Markov blanket as a holographic screen that is separating an internal and external bulk. And then the idea being that the internal and external bulks read and write classical information to the holographic screen, and then he derives a free energy principle on the basis of that, and effectively showing that after a sufficient amount of time, there is a degree of entanglement, which classically would be read as generalized synchrony between the inside and the outside. So if you could actually understand the free energy principle without any reference to Bayesian mechanics and self-evidencing, purely in terms of synchronization of chaos or chaotic synchronization or generalized synchronization between the internal and the external states on a synchronization manifold. And on that synchronization manifold is where the free energy minima live. And so you have itinerant, usually solenoidal-like dynamics on that synchronization manifold, which I repeat, would provide a purely classical dynamical systems perspective on the free energy principle. I'm saying that for you in case you wanted to think about it in terms of dynamical systems analysis.
Very small follow-up question. So do you think the world is linear or non-linear?
I think the world is non-linear.
How non-linear?
Is that a trick question? I don't
Yes.
know how to think about that.
Okay, while I'm strolling to where the next question is and learning, okay, over there, I'm gonna throw another one at you, Karl, or revisit the one I just asked. So, suppose I want to know. Suppose I'm a scientist. Just imagine that, and I'm studying a system, and I want to know if this system is doing active inference or doing, quote unquote, doing free energy minimization. is there something embedded in the formalism here that could give some predictions on the signatures that you might expect to see? So you were talking about the separation, the solenoidal flow, and the gradient descent. So that would be a complex, an oscillatory component and a decaying component. Maybe if those are fluctuating in time in their magnitude, then there's a spectral signature there. Maybe if you switch off one part of it, as you were kind of going with the sleep example, I think there's some phasic elements. Do you think that there could be there's the prediction errors, right? There's predictive processing and that part of the framework, but in terms of the dynamics, can we generate some predictions about certain characteristics, spectral or other dynamic signatures of a free energy minimizing system, and then go and see if we can measure them and test that hypothesis?
Yes, it's a great question. I think you could approach that at two levels. There's a very sort of low-level mechanistic consequence of free energy minimization, and that inherits from Jaynes's maximum entropy principle, or the minimization of complexity. So in brief, if you imagine a sort of a free energy potential landscape, and you've got gradient flows on that landscape, the entropy corresponds to the curvature of the landscape, which means that by construction, the free energy minima that now represent the non-equilibrium solutions have a low curvature by construction. So, if you're in machine learning, what that means is if you want to use a right objective function, use the variation of free energy, because by definition, you can't have sharp minima. Sharp minima would have a high curvature and a low entropy. So that's why variational autoencoders work better than without the sort of without this sort of complexity penalty or maximum entropy imperative. So what does that mean for the dynamics? Well, what we're saying is that the system, any dynamical system, will be found in the vicinity of a free energy minima, which means that the curvature, the Hessian, will be small. What does that mean for the Jacobian? Well, it means that the real parts of the eigenvalues those parts that approach zero from below will become increasingly prevalent. What does that mean? It means you'll get critical slowing. So as you reach your free energy minima, the curvature goes down, the conditional entropy, if you like, goes up, the entropy of the Q, the Jaynes entropy, if you like, goes up, and all the real parts of your eigenvalues on the order parameters or the principal leading eigenvalues all start to approach zero from below. So things decay very slowly, so you get long range correlations. So what you'd expect is the emergence of sort of scale free or scale invariant dynamics with critical slowing as the system approaches its free energy minimum. So that's one very simple thing, which is why that motivates a focus on that kind of aperiodic or scale invariant, and it provides, I think, an interesting take on self-organized criticality, because we're talking about self-organization under the free energy principle, and that entails critical slowing. So that's one very simple explanation of self-organized criticality. The other direction you could take it is it speaks to what we were talking about yesterday and today, in fact, in terms of deep generative models and the separation of temporal scales. So as soon as you get a separation of temporal scales that underwrites your coupling back to the world, your joint system now becomes non-Markovian. So I'd expect to see, if I was looking at you, and perhaps I should just stand back for a moment and just observe something quite fundamental. Because I can never observe your internal states, I'll never know whether you're self-evidencing. I'll never know whether you're reasoning or you've got any Bayesian mechanics going on. All I can see are your active states. So I can only infer what you're doing on the inside. And likewise, I can only infer the generative model that you're using to underwrite your, so it's all as if. So these are just inferences. I can never actually know. But if you're asking me, how could I tell that you had a deep generative model as opposed to a very simple, shallow generative model, I would be looking for dynamics in your behavior, which could be, electrophysiological behavior, or it could be actually motoric behavior or prosocial behavior, that was non-Markovian, or at least semi-Markovian, that would be a signature of a deep generative model with separation of temporal scales. If I was a physiologist, I'd be looking for instances beyond homeostasis. I'd be looking for evidence in your behavior that was more allostatic in nature, that you were anticipatory in your responses. And again, in a sense, speaking to sort of long-range correlations, because what you do now depends very much upon not just the immediate past, but the distant past and the context and what you have learned. Because again, the learning is another aspect of the separation of temporal scales. So that would be another, another sort of signature I'd be looking for. I'd be looking for sort of anticipatory behavior, planning-like behavior, evidence you had intentions that were free of the moment. And of course, if you pursue that route, we're talking about exactly what we're talking about this morning in terms of computational phenotyping from Chris and Andrea. We're talking about the game of inferring what kind of generative model, what kind of thing is this when I can only observe its actions on me and the rest of the rest of the usually a shared world. And you could take that into theory of mind and indeed right to the level of consciousness. And if can I infer you are conscious? Of course I can't, but I can infer it, but I never actually know.
Thanks.
Thanks for the talk. It was wonderful. So my question is, I wonder how would you explain the behavior of suicide by the whole theory framework? Thanks.
Yeah, so there are a number of papers that deal explicitly with suicide from the point of view of active inference. It's a really interesting issue. I remember starting last night's lecture with the cautionary note. The free energy principle just says if something exists, then it can be described as possessing these properties. It does not say that to exist, you have to do this. So that, when applied to the notion of suicide, existing is not necessarily motivated by avoiding death. All you need to do is to avoid surprise. And if I find it more surprising to live than to die, when I project into my counterfactual future, it is entirely base optimal for me to kill myself. Entirely base optimal. So least surprising, especially if I believe I'm an altruistic person and I'm dying for somebody else. I'm sacrificing myself, say, in a combat arena for my brothers in arms. So if I believe I am the kind of thing that will sacrifice myself for my conspecifics, my brothers in arms, then it would be very surprising if I didn't kill myself. You could also apply exactly the same arguments to end of life care, or people who would like to take control over the way that they pass if they have a terminal illness. So suicide in its various forms is, to my mind, unsurprising and quite a natural thing to do. But it does also speak to, we only behave in a way in which we don't surprise ourselves. So it depends very much upon your inferences. How would I behave in this situation? And that's basically what you do. And of course, that's a bit context sensitive. And I can imagine certain contexts in which I would, if I were to save my children, for example, I would, I can imagine it would be more surprising not to sacrifice myself than to sacrifice myself.
Last question is over here. Sorry, we're at time.
Thank you again for the lovely lecture. So I'd like to ask a question a bit more about how we understand the mind in the context of active inference and in free energy principles. So something that became apparent to me through your lecture series is that in its essence, we require a generative model to exist, to be within our environment and to make decisions and actions. And we can model this and observe this at several scales in systems. So how do we learn about the properties of these generative models and how they exist in people, whether we can identify core similarities of like priors or policies, or in some way, what these investigations and what these conceptions can tell us about generative models in people?
Yeah, well, that's a great last question. I think probably answered on two fronts, which I think would speak to most people in this audience. I repeat, I can never see inside your brain. I can never see inside a working thermostat unless I break it and so breach its Markov blanket. I can never see inside a virus that's doing its thing. All I can do is infer. So I can only infer what kind of generative model you are using, and that inference would basically render your observed behavior the most likely. So effectively, we're trying to reverse engineer everything else's generative models. And there are a number of ways you can do that. You can become a neuroscientist or a psychologist, or do brain imaging, for example. So try to peek beneath the Markov blanket and get an idea from the structure and the anatomy, the computational architecture of the internal states that entail the structure of the generative model. And that speaks to some, very old ideas, and I think very compelling ideas. For example, in cybernetics, a good regulator theorem that to be able to navigate and control an environment in which I exist, I have to be a model of that environment. I have to have the same degrees of freedom, the law of requisite variety, as the degrees of freedom that are controllable in this. And what that means is, if I were able to dissect your brain, I should be able to discover a lot about the world that you navigate and control. And my favorite example of this is the separation of what and where streams in the brain, the anatomical separation, which you could read as a statement that that anatomical separation of what and where processing in the human brain tells you immediately that this brain lived in a world where there was a statistical or conditional independence between what and where, in the simple sense that there were objects, but knowing what an object was didn't tell you where it was, and knowing where an object was didn't tell you what it was. So if I could tell just by looking at your brain, if I was allowed to dissect it, that you came from a universe that had objects that could be in different places, but there was a conditional independence between the whatness and the whereness. So really simple. There are all sorts of other examples. The wavelength sensitivity of your eyes would also tell me you live in this kind of under this kind of radiant illumination. So just by looking at the structure of the generative model, both in space and time, with electrophysiology as well, can help you a lot in terms of reverse engineering or getting the kind of generative model. When doing it in a living subject, this is exactly what lots of people are trying to do at the moment in computational psychiatry and neurology. So designing the right kinds of experiments, a bit like the game we played today, in order to unearth the implicit generative model, or those aspects of the generative model that are leading to behaviors that you might want to remediate or understand better as an academic or treat as a doctor. So you are now applying the free energy principle active inference in a second order, a meta sense, that you're now trying to perform experiments to try and disclose the behavior of something that will enable you to make the best kinds of inference about the generative model that this subject, this patient, is actually working. That's a really difficult game, but it's something which is probably quite important to do. And I should say that we're all quite skilled at doing that, because that is theory of mind. The fact that we're talking together, the fact that you have a sense of self and a sense of other, immediately tells me that you have been quite good at making inferences about my generative models, or those of your friends, colleagues, and family, and the people that you interact with. So, great question. It's all about inferring the generative model that you are using.